All right, this lesson is called Conditional Probability. One definition to start, it is a review, okay? Recall that the probability of an event is a number indicating the likelihood that it occurs, okay? Probability. Remember, probability is always between 0 and 1, unless you put it as a percentage, then it's between 0% and 100%. So if the probability equals 0, that means that it will not occur. It definitely will not occur. If the probability, again, capital P stands for probability, if the probability equals 1, then it's guaranteed that it will occur. So I'll say will definitely occur. And if the probability equals half, well, that's halfway between 0 and 1, so it's equally likely to occur or not occur. And again, I'm just going to give you the formula for probability. Probability equals a number of ways an event occurs divided by the number of all possible outcomes. Okay, let's just copy that down again. Number of ways an event occurs divided by the number of all possible outcomes. Okay, so now we're going to do the fundamental counting principle. Okay, it says if you can do one process m ways, and you can do a second process n ways, then you can do process 1 followed by process 2 in m times n ways. So you multiply them. Okay, this extends to 3 or more steps. Ignore the voice crack. This extends to 3 or more steps. So for example 1, Jerry has 10 different shirts, he has 5 pairs of pants, and he has 3 pairs of shoes. How many different outfits can he create? We're going to use the fundamental counting principle. So we're going to multiply. Okay, we're going to multiply 10 times 5 times 3. That's the fundamental counting principle, multiply. That's going to equal 150 different outfits. Okay. Fundamental counting principle. Multiply. Okay. Example 2. The old style Rhode Island license plates consist of 2 letters followed by 3 digits. The first digit cannot be a 0. How many different old style Rhode Island license plates are there? Okay, so we got to think about this. We have 2 letters followed by 3 digits. Okay, so we have a letter and then a letter. Then we have a digit that's not 0. Then we have any digit. And then we have any digit again. Okay, so let's think about this. There's 26 letters in the alphabet. So there's 26 possibilities here times 26 possibilities here times the digit. The first digit cannot be 0, it says. So that means you can have 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 possibilities. The next digit has no restriction, so it can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 possibilities. And then the same thing for the last digit. There's 10 possibilities. You multiply those 5 numbers. and you get 608,400 possible license plates. The next one, how many different old-style Rhode Island license plates are there that use 2 different letters and 3 different digits? Oh boy. In other words, no characters used more than once. Okay, so we have 2 letters. So the first letter, there's 26 possibilities. The question is, how many possibilities are there for the second letter if you do not use the same letter twice? So let's say the first letter is A. That means the next letter can be anything from B to Z, so there's 25 possibilities. Then we have the first digit. There's 3 digits. Remember, the first digit cannot be 0. So there's 9 possibilities. And now if you think about it, okay, so the first digit cannot be 0. That's why there was 9 possibilities. Now the next digit can be 0, so we're going to add in a 0. But if we don't repeat any digits, then how many possibilities are there? So in other words, let's say the first digit was a 4. The 4 goes away. And now we have 1, 2, 3, 4, 5, 6, 7, 8, 9 choices still. And let's just pretend that that digit was a 7. So the 7 goes away. And now we have 1, 2, 3, 4, 5, 6, 7, 8 possibilities left. So those numbers are going to multiply. That's going to give you 421,200 possible license plates. Okay. Now the next few questions talk about cards. And I did put up a document that has all the different types of cards and it's color coded. So let's say you draw a random card out of a standard deck of cards. What's the probability that the card is an ace? Okay. So the probability that the card is an ace equals, well, there's 52 cards in a deck of cards, so it's going to be out of 52. And 4 of them are aces. So the answer is going to be 4 over 52. Let's simplify that fraction to 1/13. And let's also write that as a decimal because I could ask you for it as a fraction. I could ask you for it as a decimal. So as a decimal, let's say approximately 0.077. Let's also put it as a percentage because I could ask you for it as a percentage. As a percentage, let's say approximately 7.7%. Okay? Again, refer to the document I posted about cards in case you don't know how many cards there are in a deck of cards or how many aces there are. There's 52 total cards in a deck of cards, and 4 of them are aces. All right, the next thing you have to know is what's called the general addition rule. Okay, so the general addition rule says the probability of 2 events, A or B, equals the probability of A plus the probability of B minus the probability of A and B both occurring at the same time. Okay, now the reason why you have to do that is because if you don't subtract it out, you're going to be double counting things, which will mess up your answer. Okay, so example 5. You draw a random card out of a standard deck of cards. What is the probability that the card is red or a king? So here's how we're going to do it. The probability that it's red or king equals. First, we're going to do the probability that it's red. So there's 52 cards in a deck of cards, and 26 of them are red. There's 26 red cards, and there's 26 black cards. And then let's do the probability of a king. All right, so just to backtrack really quick, there's 52 cards in a deck of cards, 26 are red, and then there's 4 kings, so I add 4 to 52. Okay? So 26 red cards, 4 kings, and you have to subtract out the repeats, meaning you have to subtract out the cards that are both red and kings, and there's 2 of those. Okay? So again, this is the probability of a red card plus the probability of a king minus the probability of the red kings combined. Okay? You can't double count. So when you add those together, you get 28 out of 52. 26 plus 4 is 30, minus 2 is 28 out of 52. Simplify that fraction to 7/13. Put the answer like that, and we'll put it as a decimal, so approximately 0.538. And let's put it as a percentage. Let's say approximately 53.8%. Example 6. You draw a random card out of a standard deck of cards. What's the probability that the card is a face card or a heart? Okay. So the probability of a face or a heart. So first we're going to count the face cards. Again, I have the picture online. There's 12 face cards, okay? The kings, the queens, and the jacks. There's 12 face cards. There's 13 hearts, so we're going to add 13 out of 52. And then we're going to subtract out the repeats, the ones that are both hearts and faces, and there's 3 of those. So that'll give you 22 out of 52. Let's simplify that fraction to 11/26. Let's put it as a decimal, 0.423. And a percentage, 42.3%. Next up is the general multiplication rule. It says the probability of A and B both happening equals the probability of A times the probability of B. Okay. So now let's do some examples based off of this. Example 7. You draw 3 random cards out of a deck of cards without replacement. That means you take one out and you leave it out. You don't put it back in. You take it out, you leave it out. What's the probability of getting 3 aces? Well, first there's 52 cards, and there's 4 aces, so 4 out of 52 times. So the idea is you took an ace out and you left it out. So now there's only 51 cards left to choose from, and since you already took out 1 ace, there's only 3 aces left. And now the next one, again, you're taking the cards out, you're leaving them out. So there's only 50 cards left now, and there's only 2 aces left. 4 times 3 is 12, times 2 is 24. Over 132,600. If we simplify that fraction, it comes to 1 over 5,525. Which, as you can see, that's very unlikely to happen. If we put it as a decimal, that's going to be approximately 0.00018. If you put it as a percentage, it's approximately 0.018% chance of happening. Very, very small. Okay. Example 8. A fair coin is tossed 4 times. Fair coin means it's equally likely to be heads or tails. What is the probability of getting 4 consecutive heads? Okay? The probability of 4 consecutive heads equals the 1/2 chance of getting heads times 1/2 on the second toss times 1/2 on the third toss times 1/2 on the fourth toss. Every single time, there's a 1/2 chance of getting heads. So if you multiply that out, you get 1/16. As a decimal, it's exactly 0.0625. As a percent, it's exactly 6.25% chance of happening. Example 9. A jar contains 8 blue pens, 4 black pens, and 3 red pens. If 2 pens are drawn without replacement, meaning you take it out and you leave it out, what's the probability that the first pen is blue and the second pen is black? The probability of blue and black equals if you add up the pens, there's 15 pens. The chance of getting blue is 8 out of 15 because there's 8 blue pens. And now the idea is you take that pen out and you leave it out, so now there's only 14 pens left to choose from. And the probability of getting black on the second try would be 4 because there's 4 blacks. Multiply those together, you get 32 over 210. Simplify that fraction to 16 over 105. As a decimal, that'll be approximately 0.152. As a percentage, that's 15.2%. Okay, we have 2 more pages, or 1.5 pages. A conditional probability table. Is defined for a set of discrete and mutually dependent random variables to display conditional probabilities of a single variable with respect to the others. That's what the next 3 examples are based off of. Conditional probability tables. So here's example 10. You have to be careful, these are tricky. What percent, part A, what percent of students are male biology majors? So what percent of all students, there's 150 students altogether. What percent of them are male biology majors? So it's going to be 40 over 150. I'll give you approximately 0.267, which is approximately 26.7%. It doesn't tell you where to round, so I'm just going to do 26.7%. Part B, what percent of females are chemistry majors? Okay, so now we're talking about just the females. Just the females. So we're doing it out of 59 because there's 59 females. So this is going to be based off of 59, not 150. We're not basing it off of everybody. We're just looking at the females. What percent of those females are chemistry majors? 20 over 59. That's going to be approximately 0.339. So as a percentage, it'll be about 33.9%. Part C, what percent of physics majors? So now we just want the physics majors. So we're basing it off of 40. We're just looking at the physics majors now. It's based out of 40 now. What percent of those are male? So 16 out of 40. Equals exactly 0.40, which is exactly 40%. So fast now, part 11A. What percent of students are 8th graders that prefer math? So this is based off of everybody. So it's based off of the total number of 266 students. And we want just the 8th graders that prefer math. 72 of them. So 72 out of 266. That equals 0.271. (27.1%). Part B, what percent of 7th graders prefer history? So we only care about the 7th graders, so when they're basing this off of 102 students. Seventh graders, what percent of them prefer history? So we just want the history, which is 36 over 102. Approximately 0.353. Which is 35.3%. Part C, what percent of students that prefer English? So again, we're looking at just the English preferences, which is going to give you 85 for the denominator. So this one's based off of 85. What percent of them are 8th graders? So just 47. That's going to give you 0.553. 55.3%. Okay. And now we have one more, example 12, just to finish it off. What percent, so this is talking about salaries and education levels. What percent of people finished college and make over 30,000? This is talking about everybody. What percent of everybody? So it's going to be out of 1,200. What percent of them finished college and make over 30,000? So it'll be 245 out of 1,200. That's going to give you 0.204. 20.4%. What percent of people with less than a high school education? So this is going to be based off of 107 people. Make 20,000 to 30,000. That'll be 36 over 107. Okay. Which is approximately 0.336, which is about 33.6%. All right, one more. What percent of people that make under 20,000? So we just gave out those people. It's going to be based off of 296. Have only a high school education, so it'll be 112. We're assuming it's just 112. 112 over 296. .378. 37.8%. So you have to be very careful for the denominator for these. What are you basing this off of? What is the sample size of the survey? And that is the end of that lesson. That lesson was called Conditional Probability.